Hi, this is Karthikeyan, your chemistry mentor. In brief, if I introduce myself, means I'm having 10 years of teaching experience. So many of my students joined in NITs, and some of my students got government medical seats also. So today we are going to discuss about D block elements or transition elements. So what is the weightage of these D block elements? This D block elements in NEET as well as in JEE means it is having 5 to 8% of weightage, and 2 to 3 bits will come from this topic in each and every exam. So let me introduce about these D block elements. So in this, what I have to discuss means the basic terminology like a D block elements. What is meant by D block element? What is transition elements? What is non-transition elements? What is meant by transition? What are the coinage elements? What are the coinage elements? What is the general electronic configuration? What is a pseudo inert gas configuration? What is a stable electronic configuration? What is the anomalous electronic configuration? About this in brief we have to discuss. These are the basic terminology in D block. Next, physical properties we have to discuss here. Physical properties. In physical properties also, atomic and ionic radius in series as well as in groups. Next, lanthanoid contraction. Next, actinoid contraction. Next, and its consequences, lanthanoid contraction consequences, actinoid contraction consequences. Next, ionization energy in series, in groups, and comparison between S and D block about this ionization energy. Next, how this ionization potential 2 will varies in case of chromium and manganese and copper and zinc. Next, what are the densities? What is enthalpy of atomization? Next, what is a melting point and boiling points? Next, we have to discuss here chemical properties. Chemical properties. So in chemical properties, what I have to discuss means variable oxygen states, reduction potential, standard reduction potential. So how this standard reduction potential, chemical reactivity are correlated with each other, that thing. Next, magnetic property. Next, crystal field splitting in octahedral complexes and tetrahedral complexes. Next, formation of different colored ions, formation of colored complexes, and formation of interstitial compounds, formation of alloys, and its catalytical activity we had to discuss. In chemical properties, we have to discuss these and all things. Next, what is another topic is some important compounds like potassium permanganate. Next, potassium dichromate. In this commonly, what are the points we have to discuss means preparation. Preparation of potassium permanganate, preparation of potassium dichromate. Next is physical properties. Physical properties of potassium permanganate and physical properties of potassium dichromate and its structures, both of these structures, and chemical properties we have to discuss in each case. Next, we have to go with this F block or inert transition elements. What is F block or inert transition elements means? See here. So F block or inert transition elements means here. So here also some of the basic terminology we have to see. What is F block? What are the general electronic configuration in that? What is a stable electronic configuration? And F block series, how they are divided into 4F series and 5F series. That means lanthanoids and actinides. What are its physical properties? Physical properties in that atomic and ionic sizes and oxidation states. Okay, next chemical properties we have to discuss in detail. Chemical properties means basic strength, solubility, color, magnetic property, extraction of 4F elements like lanthanides, and its chemical reactions. About this we have to discuss. Then coming to the point, first of all, let me introduce what is meant by D block. D block elements. D block elements briefly divided into 3D series elements, 4D series, 5D series, 6D series. Based on what is divided into 3D, 4D, 5D, 6D means, due to entering of differentiating electron 1, 2, 3, 4, for example, 5. If the differentiating electron, and this is, see here, this is 3D thing, this is 4D, this is 5D. If one more, if a drawn means this is 6D. If the differentiating electron enters into, if the differentiating electron enters into 3D level means, so in all these cases, see, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. In all these cases, the differentiating electron enters into 3D level only. That's why these are kept in 3D series. Okay, for example, scandium. What's its electronic configuration? Its atomic number is 21. Argon, 3D1 4s2, 3D2 4s2. Okay, 3D3 4s2, 3D5 4s1, 3D5 4s2, and 3D6 4s2, 3D7 4s2, 3D8 4s2, 3D10 4s1, 3D10 4s2. That means the differentiating electron enters into 3D level here. Okay, next, if the differentiating electron enters into 4D level means 4D orbital means that is called as 4D series elements. Yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver, cadmium. This and all will comes under 4D series. If the differentiating electron enters into 5D, 5D means if they enters into 5D means, then it is called as 5D series. Lanthanum, hafnium. Okay, next tantalum, tungsten, rhenium, osmium, iridium, platinum, aurum, silver will comes under this. Next, if the differentiating electron enters into 6D series means, 6D orbital means actually 6D level, then it is called a 6D series, like actinium, rutherfordium, dubnium, siborium, borium, osmium, meitnerium, dramstanium, rhanginium, copernicium. Like this, it is divided. So 3D, 4D, 5D series based on the differentiating electron enters into different d orbital, it is divided into 3D, 4D, 5D, 6D series. Actually, if you see according to IUPAC nomenclature, first A group, second A group, first A group means that is number 1 group, second A group, that is number 2, this is 3, third group, this is 4th group, this is 5th group, 6th group, this is 7th group, 8th group, 9th group, 10th group, 11th group, 12, and then 13, 14, 15, 16, 17, 18. That means in that P block it will go. Okay, so this is according to IUPAC nomenclature. Okay, so in general, classical method, if you see, means this is first B, this is second B, this is third B, this is fourth B, this is fifth B, this is sixth B, and this is seventh B. Together, iron, cobalt, nickel, this transition triad, iron, cobalt, nickel, ruthenium, rhodium, palladium, osmium, iridium, platinum. This transition triads together is called as 8th B group. Like this, totally D block elements is divided into some series as well as in the form of groups. Next, after that, what I'm trying to explain means, what are some of the basic terms we had to discuss here. See what are the basic terms. First of all, what is D block elements? D block elements are nothing but, see, when the differentiating electron enters into n-1 D level, okay, that and all elements are called as D block elements. Elements whose differentiating electron enters into n-1 D sublevel are called as D block elements. For example, take this one, scandium, simple example, 21, atomic number 21, its electronic configuration is argon, 3D1 4s2. So after entering into NS level, it is entering into n-1 D sublevel. Okay, so the differentiating where it enters, based on that it is divided. Okay, so in all these what we call first B to second B, that means first B, second B up to 8th B group, all these are called as D block elements only. What are those? First B to 8th B, these are called as what? D block elements. The D block elements divide into transition elements and non-transition elements. Like this it is divided. What is meant by transition? So later I will explain what is meant by transition. First of all, we will see what is transition element, what is non-transition elements. Transition element means elements in its atomic form as well as in its ionic form whose d orbitals are incompletely filled. That means at least one unpaired electron like this. At least one unpaired electrons are present means, okay, those and all called as transition elements. Okay, at least one unpaired electron should be present in that. So as an example, I took here scandium, which consists of one unpaired electron, so that migration of electron will take place from lower energy level to higher energy level, higher energy level to lower energy level. So that here these are called as transition. Okay, so all except second B, remaining all group except second B, remaining all group of elements. That means second B, otherwise we can say 12th group. Remaining all elements are called as transition elements only. What is non-transition elements? Non-transition elements means d block elements whose d orbital completely filled in its atomic as well as in the form of its ionic states are called as non-transition elements. So before losing of electrons, after losing of electrons also, the species which are having completely filled d orbitals, those are called as non-transition elements. See here, zinc, cadmium, mercury, in its atomic form, first of all, see, atomic forms. When these are in neutral form, its electronic configuration schema argon 3d10 4s2. This is 4d10, krypton 4d10 5s2, cadmium electronic configuration. Mercury, xenon 5d10 6s2. Atomic form completely filled d orbital. There is no unpaired electron here. Next, ionic forms we'll see. Ionic form, if you see, means after losing 2 electrons, argon, this is 3d10 4s0, this is krypton 4d10 5s0, this is 5d10 6s0. So after losing 2 electrons from here, 2 electron from here, 2 electron from here, so zinc plus Zn plus 2, cadmium plus 2, mercury plus 2, all are having completely filled d orbitals only. That means there is no unpaired electron. That's why these elements, second B or 12th group element, do not show any transition. So very, very important bit here this is. Okay, next. This is about transition elements. Now what is meant by transition, that we have to see. What is transition? How it will take place? So as a consequence transition, what happens? First of all, see, here I'm taking one complex, that is potassium hexacyanoferrate. Potassium hexacyanoferrate will take means in that potassium, this is potassium, and then after potassium, it is nothing but counter ion. This is counter ion, and here this is C. These are ligands. These are ligands. Next, this is nothing but central metal atom. So for example, central metal atom is here. Ligands are now approaching towards this central metal atom. So central metal atom having some d orbital, in that some electrons are present. These are the electrons. So d orbitals always degenerate orbital. Degenerate orbitals means orbitals whose energy and as well as shapes are same energy and same shapes contained orbitals are degenerate orbitals. Okay, there is no difference in their energy levels. Now whenever these ligands will comes out with electrons, already the electron which are present in the d orbitals, these two will get repel with each other. Due to that repulsion, the degeneracy of this d orbital will get disturbed and will get splits into like this Ez orbitals and T2z orbitals. For example, so Ez and T2z, this Ez is nothing but high energy level because of experiencing the high repulsion force from these ligand electrons. It occupied highest energy level because of low experience of this T2z orbital. It will occupies lower energy level. This will take place in octahedral complexes. In tetrahedral complexes, quite opposite this one, it will happen. That means T2Z will go in the upward direction, EZ will occupy the lower energy levels. Okay, like this it will take place, T2Z and EZ. Now, so see here, whenever these ligand electrons will approach us towards to this center metal atom, the degeneracy of this d orbital of center metal atom will be disturbed and it will split into like this. Now see, 4 electrons I assumed here, that 4 electrons I'm putting here. After putting these 4 electrons, what happens? See, so these lower energy level to higher energy level, they will migrate. How they will migrate? By absorbing certain energy from the visible region. Energy from the visible region, it absorbs and it will go to the next highest energy level, EZ level. After going there, it will feel instability. From there on, again has to come down. How it will come? What energy it gained before, that releases in the form of some light, some colored lights, complementary colors. In the form of complementary colors, it releases, and then it reaches to the stable state T2Z. See, it is absorbing certain amount of energy from the visible region and releases certain amount of energy. So that will be appears in the form of different colors. That means this migration of electrons is nothing but transition. Due to the transition, d block elements exhibits variable colors, variable valencies, variable oxidation states, variable magnetic properties. Variable magnetic properties means like a paramagnetic property, diamagnetic property, like these different properties it will exhibits. Okay, next if you see here, general electronic configuration, you have to see here, general electronic configuration. What is the general electronic configuration of these d block elements? N-1 D1 to 10, N-1 D1 to 10, NS1 to 2. This is its general electronic configuration. N-1 D1 to 10, NS1 to 2 is the general electronic configuration. Now, if you apply this for 3D series, this is argon 3D1 to 10, 4s1 to 2. For 4D series, krypton 4D1 to 10, 5s1 to 2. For 5D series, xenon 5D1 to 10, 6s1 to 2. 6D series, radon 61 to 10, 7s1 to 2. For 3D series, if I apply this formula by taking as an example like a scandium, what is the electronic configuration here? Argon 3D1, 4s2. That means one electron is there now in d orbital, d sublevel, and then chromium 24, argon 3d5, 4s1. 5 electrons also present here. 5 electrons are present. That means d n-1 d level consists 1 to 10. See, 5 electrons are present. Zinc 30, argon 3d10, 4s2. That means 10. So this 4s looks like ns, and this 3d looks like n-1 d1 to 10. Okay, like that we can express the general electronic configuration, very important. Next, coming to the point, pseudo inert gas configuration. Pseudo inert gas configuration. What is meant by pseudo inert gas configuration? Species which are having 18 electrons in their n-1 level. This is ns level. 4s is nothing but ns level, and this is 3s2, 3p6, 3d. This is n-1 level. N-1 level. This is okay. This n-1 level is having 18 electrons. So species which is having 18 electrons in their penultimate shell, ultimate, this is penultimate shell. In the penultimate shell, those are called as that configuration is called as pseudo inert gas configuration. This is also important. Next, what is a stable electronic configuration? Stable electronic configuration. Stable electronic configuration means here. Okay, next see, stable electronic configuration. Stable electronic configuration. Which configurations we can say as stable electronic configurations? D5 and D10. D5 and D10 configurations, which species will exhibit means those and all we can say as stable electronic configurations. For example, see here D5 configuration. Here as an example for D5 configuration and D10 configurations, I gave some of the example here. 3D series, in the 3D series, I took a chromium as an example, whose atomic number is 24, argon 3d5, 4s1, Here it is having D5 configuration. Next, 4D series, if you see, means 4D series, molybdenum, whose atomic number is 42. Krypton 4D5, Krypton 4D5, 5s1, 4D5, 5s1, D5 configuration again. 5D series, if you see, means rhenium 75. Here, xenon 5D5, 6s2, 5D5, 6s2. Okay, so these are all having D5 configurations. D5, that means half-filled d orbitals are stable. Okay, next D10 configurations. According to exchange energies, electron exchange energies also, we can explain this. Okay, how many number of exchange energies increases means the species will be that much stable. So next, zinc and cadmium 48 atomic number, mercury 80. Its electronic configuration, if you see, means argon 3d10 4s2, 3d10 4s2. Next, krypton 4d10 5s2. Next, xenon here, mercury xenon 5d10 6s2. So in all these cases, this is exhibiting, see, zinc exhibiting 3d10, cadmium exhibiting 4d10, and mercury exhibiting 5d10 as stable electronic configurations. This is about stable electronic configuration and as well as some of the examples. Next, very important thing is anomalous electronic configuration. Very important. Anomalous. So in a simple way, we can remember this one. In 3D series, see here, chromium and molybdenum. 3D5, chromium 3D5 4s1, 3D5 4s1. Molybdenum 4D5 5s1, molybdenum 4D5 5s1. Next, niobium 4D4 5s1, niobium 4D4 5s1. Once again, see, in 3D series chromium, whose anomalous, which is having anomalous electronic configuration 3D5 4s1. Molybdenum 4D5 5s1 is having anomalous electronic configuration. Next, in 4D series, niobium 4D4 5s1 is having one more species having anomalous electronic configuration. Anomalous means nothing but when compared with the remaining all which is having different electronic configuration, which is not following Moelis diagram. So according to Moelis diagram only, we are expressing the electronic configuration. Here, these species up to 10th class level, you may be studied up these two things, chromium and copper. But in this higher classes, we have to study about all these cases, chromium and copper, and then it is copper, silver, or okay. Next, this is in a easy way we have, if you want to remember, means copper, silver, or copper, silver, or copper 3d10 4s1, silver 4d10 5s1, Rm 5d10 6s1. See, copper 3d10 4s1, silver 4d10 5s1, Rm 5d10 6s1, 3d10 4d10 5d10, 4s1 5s1 6s1. In an easy way we can remember this. Okay, whose atomic numbers are here 29, 47, 79. Next, in the 4D series, if you see, means in this way, ruthenium, rhodium, palladium, ruthenium 47 5s1, rhodium 48 5s1, palladium 4010 5s0. Okay, this is in case of 4D series. In 5D series, if you see platinum and rm, 5d10 6s0, 5d10 6s1. Once again, see the anomalous electronic configuration contained elements. Chromium, first of all, 3D series, chromium 3d5 4s1, copper 3d10 4s1. In 4D series, niobium 4d4 5s1, molybdenum 4d5 5s1, molybdenum 4d5 5s1. Ruthenium, rhodium, palladium, silver. Ruthenium, rhodium, palladium, silver. 4d7 5s1, 4d8 5s1, 4d10 5s0. Ruthenium, rhodium, palladium. Next, silver 4d10 5s1, 4d10 5s1. Okay, next 5D series, if you see, means platinum and rm, 5d10 6s0, 5d10 6s1. This is its anomalous electronic configurations. So this is about the brief introduction about all the terminology regarding these D block elements. Next, what we are going to discuss means we are going to discuss about some of the objects. Okay, coming to the objective part. Element with atomic number 111 might belong to the following group. So 111 might belongs to which group means, see for example, copper, silver, aurum, rhongenium. This is 29, this is 47, and this is 50, this is 59. Okay, that is, this is 79, this is 79, and this is 111, rhongenium. Rhongenium, if you see, means argon, krypton, xenon, radon, 5f14, 69, 7s2. 5f14, 69, 7s2 is the electronic configuration. Okay, so this 5f14, 69, 7s2 electronic configuration, if you see here carefully, see here, 5f14, 16, 7s2. It is belongs to 7th period, and 9 plus 2, this is belongs to 11th group. So 7th period, 11th group. 11th group means already we know. See, this is 11th group only. 11th group elements copper, silver, aurum, and rhongenium. So 11th group, 7th period means that is nothing but rhongenium, which is belongs to copper. In that way, we can easily identify this element. Next, second question, see. The following belongs to D block, but it is not transition element. Already we know the 12th group, otherwise second B group elements like zinc, cadmium, mercury, because of having completely filled like a 3D10, 4D10, and 5D10 completely filled d orbitals in its atomic form as well as in its ionic form. Zn plus 2, cadmium plus 2, and mercury plus 2. Because having completely filled d orbital configuration, these are not considered as transition elements even though they are present in D block. Okay, right, next. Which set of elements is transitional? Which set of element is transitional in character? So these are all bits, nothing but introductory part bits only. So together I'm explaining here. Transition element, that means transitional character which are having means from the Mendeleev period table onwards, we know iron, cobalt, nickel, ruthenium, rhodium, palladium, osmium, platinum. These are called as transition triads. Okay, so this 1, 2, 3, these and all will come under transition elements only. Why means because having at least because having one unpaired electron in their D level, we can say as these and all will undergo transition. They will show the transition properties, and these are considered as transitional elements. Next. Which of the following set of elements does not belongs to transition element? See here, iron, cobalt, nickel, transition elements only. Copper, silver, or arum, transition elements only. Titanium, zirconium, hafnium, transition elements only. Boron, aluminum, gallium, indium, thallium. This is third A group elements. Boron, aluminum, gallium, indium, thallium is third A group elements. This not comes under transition elements. Next. Let's come to the point. In the transition elements, the incoming electron occupies n-1d sublevel in preference to what they're asking. For example, see here, I'm taking this one. For example, this is ns level. After filling this ns level, okay, then the electron should go into the np level. In preference to NP level, the electrons are choosing n-1d level. n-1d. After filling this n-d only, then it will occupies NP level. That means in the transition elements, the incoming electron occupies n-1d sublevel in preference of what means NP. Next. Catalytic activity of transition elements and their compounds is due to what? Because of what reason these transition elements are exhibiting catalytic activity means because of having vacant d orbitals. Due to presence of vacant d orbitals only, they are showing catalytic activities. Next, which of the following is a transition element? Which of the following is a transition element? Aluminum is not, arsenic is also not, nickel is a transition element, nickel. These are all p block elements, aluminum, arsenic, lead, these are all p block elements, nickel only the transition element. Next, the ground state electronic configuration of chromium is against 2. So the ground state electronic configuration of chromium, if you see here chromium, whose atomic number is 24 and its electronic configuration is argon. So 3D, 4 if will take means this is actually after filling this 4s2, then the electron has to, remaining electron has to go into 3D 4 level. Okay, for example, see here 1s2, 2s2 2p6, 3s2 3p6 and 3D and then 4s if will take means. See 1s2, 2s2 2p6, next is 3s2 3p6 up to 18 electron completed. Next, the electron has to choose what? See 4s 3D. First lower energy level is 4s and then 3D level it has to choose. But after filling into 4s1, the electron is choosing 3d5. See, electron enters into 3D level. See, actually the lower energy level has to fill and then the higher energy level has to go. But in preference of this 4s, after filling 3D half filled, after half filled, halfly filled this d orbital only, it is going to 4s level. That means first of all higher energy level and then it will go to lower energy level. This is against to Haber principle. Haber principle is saying that the electron should occupy low energy level and then it has to go higher energy level. But this chromium electronic configuration is against to what principle means? Haber principle. That you have to see here. Very, very important, good bit also. Next, coming to the point, the following has a pseudo-unity gas configuration in the N-1 shell, which are having pseudo-unity gas configuration in N-1 shell. Already we discussed it. Copper, typical transition elements, copper, silver, aurum, zinc, cadmium, mercury. These are all having N in their N-1 shell, these are having unity gas, pseudo-unity gas configuration. Pseudo-unity gas configuration means what? 18 electrons in the N-1 level. For example, take this zinc, whose atomic number is 30. Okay, argon. Okay, here it is. Okay, before taking that argon, we'll take this one, is that is better. 1 second, wait. 1s2, 2s2 2p6, 3s2 3p6, 3d10 and 4s2. Right now see here, this is ns level, this is n-1d level. This n-1d level having 18 electrons. In all these cases, typical transition elements as well as zinc group, these are typical transition elements, these are zinc group. In all these cases we can see the 18 electrons in their n-1 level. This is n-1 level. So both is the answer. Next, coming to the point, electronic configuration. Which one of the following pairs of ions have the same electronic configurations? Same electronic configuration, see here, Fe+3 and Mn+2 are having same electronic configuration. How can you say this? So iron atomic number is 25, whose electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, and this is 3d5, 4s2, 4s2, 3d5. Okay, so here after losing 3 electrons, 2 electron from here, 1 electron from here, means this is 3d4, 4s0. Mn+2 also will check out here. Okay, 1 second. This is actually 26. 3d6 4s2. 3d6 4s means 2 electron from here, 1 electron from here means, so this is 3d5 4s0. 3d5 4s0. Mn plus 2. This is 25. This is again 1s2, 2s2, 2p6, and then 3s2, 3p6, and then 3d5, 4s2. 3d5 4s2. That means here 2 electrons, if it loses means 3 here, the resultant configuration will be 3d5 4s0. 3d5 4s0. See, these two species, Fe plus 3 and as well as Mn plus 2, these two are exhibiting same electronic configuration after losing 3 electrons from here and 2 electrons from here. 3d5 4s0, 3d5 4s0. Okay, clear? So in that way, we can easily identify this iron Fe plus 3, ferric and manganese Mn plus 2 are exhibiting same electronic configurations. Next, which one of the following ions has same number of unpaired electrons? Same number of unpaired electrons as those present in vanadium plus 3. So vanadium means, see here, vanadium means nothing but scandium, titanium, vanadium. Vanadium is 23, whose electronic configuration is argon. Okay, and this is 3d3 4s2. What they're saying, vanadium plus 3, that means 2 electron from here, 1 electron from here, it loses means. So what is the resultant configuration? 3d2 4s0. See, 3d2 4s0. This configuration who are having, they're asking here. So nickel plus 2 it is having. See how nickel plus 2. Nickel, if you see, means nickel plus 2. Cobalt 28 is the atomic number, argon, and we can say this is 3d8 4s2. After losing these 2 electron from here, then what is the configuration? 3d8 is the configuration. 3d8. 1 2 3 4. That means 1 2 3 4 5 6 7 8. See here how many number of unpaired electrons? 2 unpaired electrons we are having. Here also 2 unpaired electrons only we are having. 2 unpaired electrons. What they're asking, see here, ma. So which one of the following ions has same number of unpaired electrons as those present in vanadium plus 3? So vanadium plus 3, how many unpaired electrons it is having? Means 2 unpaired electrons it is having. 2 unpaired electrons it is having. So in the similar way, nickel plus 2 also having 2 unpaired electrons only, these two. Okay, like this easily we can find out this. Next, coming to the next point. In the following pair of D block elements, the first member is liquid. The first member is liquid at room temperature, and the second member is mostly available in earth crust. What are the pair of elements they're asking? The pair of elements are nothing but mercury and iron. Mercury is a liquid at room temperature. Iron is found in earth crust. So this is the answer. Next, if you see here, transition metals are colored due to the following electronic configuration. Because of what electronic configuration these are colored? Due to DD transitions. Due to DD migration, these are colored. Next, which one of the transition metal ions have no unpaired electron? They're asking. Which transition metal ions have no unpaired electron? No unpaired electron means titanium, we can say easily. So how it is? Titanium belongs to, its atomic number is 22. So argon, we can say 3d2 4s2. So what 4 electrons are present? Those and all it lasts here. So these 2 electron, when it loses means there is a configuration what? The 3d0 4s0. No unpaired electron. See, there is no unpaired electron here. So that we can say, so titanium plus 4 is the answer. Next, the metal ion which does not form colored compounds. Which does not form colored compounds means zinc, we can say. Why it is? Zinc is having completely filled D10 configuration. Because of that reason, this is called as non-transition also. No? So second B group, so it won't form any colored compounds. That is the example. Next, transition metals are often paramagnetic owing. Because of what these are paramagnetic? Transition metals, why these are paramagnetic? Because of the presence of unpaired electron. Because of the presence of unpaired electrons, these are paramagnetic in nature. Next, orbital splitting. In the presence of strong electrical field, the following set of orbitals are not degenerative, which are not degenerate in the strong electric field even. So here see, because of a different oriental axis, this 3D XY and 3D Z square, 3D XY, 3D Z square do not shows any degeneracy with strong electric field also, because of having different orientation axis. 3D XY and as well as 3D Z square do not shows any degeneracy for strong electric field. Next, which transition metal is known as strategic or wonder metal? Which is strategic or wonder metal means titanium is the wonder metal. Why? Because of its strongness or strength. It is strong like steel. It is non-corrosive, and as well as it is light in weight. So because of these properties, titanium is considered as wonder metal or a strategic metal. Okay, so that's about the objective part regarding this introduction part. So in the next part, we are going to discuss about the physical properties, and then the next part we are going to discuss about the chemical properties, and then some of the important compounds like potassium permanganate and potassium dichromate we are going to discuss. And then the next part will be about F block elements like lanthanides and actinides. Thank you very much for watching my video. Thanks a lot.